Welcome to our series on radome and bumper testing, where we cover everything you need to know about radome testing and the usage of the powerful QAR50 tester. Our experts at Munich and Memmingen have put a lot of effort into the traceability of the measurement results. Let me introduce our certified calibration setup in Memmingen and how the values on the verification samples are actually generated. On the right-hand side of the slide, you can see the accredited quasi-optical setup. On the left-hand side of the slides, you can see a schematic drawing of that actual setup. So we are using two corrugated horn antennas, which are transmitting or receiving on two mirrors. And those two mirrors are focusing the beam on our device on the test. So that's basically one of the most precise measurement setups you can get for material characterization. And we also have the accreditation certificate, which you can also find in the link that is shown here on the slide. What are the advantages of such a setup and why is it used? It's used because it's super precise. So you can't use a higher precision with many other setups. So either you're using the quasi-optical setup or you're using a waveguide-based setup if you want to perform material characterization. The problem is it's difficult to set up and it's also difficult to operate. It's very sensitive in terms of the alignment, and also the calibration is quite crucial. So only experts can actually operate and measure with such kind of setup, and you can't use it really in production. Also, the components used here are very expensive and very sensitive. So again, another factor that speaks against using these kind of setups in a production environment. However, the setup is perfect for homogeneous and flat materials. So you can use it for material characterization, for example, but it struggles with curvature. When we look at the QAR50, we probably don't reach the same level of precision with the QAR50 that we reach with the quasi-optical setup, but it's still super precise, much simpler to set up, and even non-experts can operate it. So the alignment here is also less crucial, as you've probably seen in some previous videos, and also the calibration is super simple, including the normalization, which is very simple as well. The components here are designed to be a bit more robust, so still you can't play football with it without hurting it, but they are more robust than the components in the quasi-optical setup. So that means the instrument QAR50 is also well suited for flat and homogeneous materials, but does not so much struggle with curvature as the quasi-optical setup does. So looking in the traceability, accreditation, precision, accuracy, what can we actually expect from such a setup? So this is an extract from the table that we are accredited to, which is available under the link that was provided in the previous slides. And we can have a look at the respective lines where we find the values that we're actually looking into. So starting with transmission loss, what is the accredited measurement accuracy that we can reach with this setup? So we can see in this line 0 dB to 10 dB, 70 to 85 gigahertz, we are reaching an accuracy of 0.1 dB. So quite simple, we find the answer directly looking here. It's a little bit more complicated with the reflectivity. So we find the answer here below. So again, 70 gigahertz to 85 gigahertz, we are finding an uncertainty of the measurement, uncertainty factor of 0.026. So the measurement results that we are getting are usually in dB. So we need to calculate that uncertainty factor in dB. A standard radome has a reflectivity of around about minus 20 dB. So that means 10% reflectivity converted to dB is around about minus 20 dB. So now we take this uncertainty factor of plus minus 0.021 on this reflectivity factor of 0.1, which corresponds to the minus 20 dB. And we see if we add it, we get minus 18 dB. And if we subtract it, we get minus 22.6 dB. So that means for a standard radome with 10% or minus 20 dB reflectivity, we have an uncertainty of minus 2.62 plus 2 dB. So when we compare these two values, 0.1 dB and 2.6 or 2.0 dB, to the values that we get with the QAR50, We see at minus 15 dB, we have an uncertainty of round about 3 dB, which is not too far away from the 2.5 dB that we had with the quasi-optical setup. And in terms of the transmission loss, we also have a quite good accuracy compared to the VNA setup. So the QAR50 does not really have to hide when being compared to the highest precision that we can reach with standard test and measurement equipment.